everyone, welcome to the channel TechSpot. This is me Harish Gaupale. So guys, in this video I'm gonna tell you how we can implement simple logic gates such as AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate, NAND NOT gate by using simple 2:1 mux. So let's get started with first gate, that is AND gate. Now you can see the truth table of AND gate. AND gate having two inputs A and B and one output. What it tells, if both inputs are high, then only output will be high, otherwise output will be low. So to implement this AND gate, we'll draw 2:1 mux. You can see the diagram of 2:1 mux on my screen. 2:1 mux need one select line, two inputs and one output. So to implement this AND gate, I have selected A input A as a select line for this 2:1 mux. So if you see the working of this 2:1 mux, if select line A is equal to 0, the output Q will be equal to 0 because in input I am providing 0. And if you see truth table, when A is equal to 0, in output I am getting 0 only. Okay. Similarly, when A is equal to 1, the output Q will be equal to B. So if you see the truth table, when A is equal to 1, whatever value inside in B, that is 0, 1, same I am getting in the output. Okay. So as per the truth table of AND gate, we are getting output from this 2:1 mux. So this is how we can implement AND gate by using 2:1 mux. Now guys, we are going to implement the OR gate. You can see the truth table of OR gate. What it tells, if any input is high, output is high, otherwise output is low. So to implement this OR gate, we'll draw 2:1 mux. Here you can see 2:1 mux, which is having one select line, two inputs and one output. As we know the working principle of 2:1 mux, based on select line it will transmit input to the output value. So if my select line A is equal to 0, in the output I will get the value of B. If you see truth table, when A is equal to 0, whatever the value present in B, 0, 1, I am getting in the output. Similarly, if select line A is equal to 1, then the output Q will be equal to 1. If you see truth table, so for A, select line A is equal to 1, the output is 1 on only, though the value of B is 0, 1. So that is the reason I have connected input 1 for select line A is equal to 1. So as per the truth table of OR gate, we are getting output from this 2:1 mux. This is how we can implement OR gate. Okay. Now guys, we are going to implement NAND gate by using 2:1 mux. So here you can see the truth table of NAND gate. It is nothing but inverse of AND gate. Okay, so to implement this NAND gate, we'll draw 2:1 mux. Here you can see on screen I have drawn a combination of 2:1 mux. This first 2:1 mux act as a NOT gate. If you see the working principle of this NOT gate, so if B is equal to 0, the output B bar is equal to 1. That means simple, if I am giving input B, I will get B bar. Okay, but to implement this NAND gate, the main mux is this mux. So for this 2:1 mux, I have selected select line A for this 2:1 mux. So means if select line A is equal to 0, the output Q will be equal to 1. So if you see the truth table, A is equal to 0, in output I am getting 1 only. So that is the reason I have connected input as a 1. If select line A is equal to 1, the output Q will be equal to B bar. If you see the truth table, so if A is equal to 1, the output is equal to B bar. B is equal to 0, in output I am getting B bar. If B is equal to 1, 0. That means that is the reason I have connected select line A is equal to 1 input as a B. So as per the truth table of NAND gate, we are getting output from this 2:1 mux. So this is how we can implement NAND gate by using 2:1 mux. So now we are going to implement NOR gate by using 2:1 mux. So you can see the truth table of NOR gate. It is nothing but inverse of OR gate. Okay, so to implement this NOR gate, we'll draw 2:1 mux. Here you can see on screen 2:1 mux. Here I have selected input A as a select line for this 2:1 mux. If we see the working principle of this 2:1 mux, so if select line A is equal to 0, the output Q will be B bar. So if we see in truth table, you can see when select line A is equal to 0, in output I am getting B bar. B is 0, output is 1, B is 1, output is 0. Similarly, if select line A is equal to 1, in the output Q will be equal to 0. If you see the truth table, when select line A is equal to 1, in output I am getting 0 itself, though the value of B is 0, 1. That is the reason I have connected 0 input for select line A is equal to 1. So as per the truth table of NOR gate, we are getting output from this 2:1 mux. This is how we can implement NOR gate by using 2:1 mux. So now we are going to implement XOR gate by using 2:1 mux. Here you can see the truth table of XOR gate. What it tells, if both inputs are same, then output will be 0, otherwise output will be 1. Or we can say if both inputs are inverse, then output will be high, otherwise output will be low. So to implement this XOR gate, we will draw 2:1 mux. Here you can see 2:1 mux. For this 2:1 mux, I have selected input A as a select line. So let's see the working principle of this 2:1 mux. If select line A is equal to 0, the output Q will be equal to B. So if you can see on truth table, when select line A is equal to 0, whatever present value inside the B, we are getting in the outputs. That is the reason I have connected select line A is equal to 0, B as an input. If select line A is equal to 1, then output Q will be equal to B bar. So you can see on truth table, when select line A is equal to 1, in output we are getting B bar. Means if 0, B is 0, the output is 1, B is 1, output is 0. So as per the truth table of XOR gate, we are getting output from this 2:1 mux. This is how we can implement XOR gate by using 2:1 mux. So now we are going to implement XNOR gate by using 2:1 mux. You can see the truth table of XNOR gate. What it tells, if both inputs are same, the output is high, otherwise output is low. Okay, so to implement this XNOR gate, we'll draw 2:1 mux. You can see the 2:1 mux. Here I have selected input A as a select line for this 2:1 mux. Let's see the working principle of this 2:1 mux. So if select line A is equal to 0, in output Q will be equal to B bar. If you see the truth table of this XNOR gate, if input A is equal to 0, in output I am getting B bar. B is 0, output is 1, B is 1, output is 0. Similarly, if select line A is equal to 1, the output Q is equal to B. You can see on truth table, A is equal to 1, that time whatever value present inside the B, 0, output getting as a same. So that is the reason I have connected for select line A is equal to 1, B is the input. So as per the truth table, this 2:1 mux, we are getting same output. This is how we can implement XNOR gate. Now we'll implement NOT gate by using 2:1 mux. So here you can see the truth table of NOT gate. If A is equal to 0, output is equal to 1. And here you can see the 2:1 mux. So here we have input as a A only. So that is the reason for this 2:1 mux, I have selected a select line as an input. So if A is equal to 0, the output Q will be equal to 1, and if A is equal to 1, output Q will be equal to 0. So this is how this 2:1 mux satisfies the NOT. So here we have implemented all the logic gates by using 2:1 mux. So we'll stop here. Thank you so much for watching this video. If you like this video, then please subscribe the channel and share with your friends. Thank you so much.